Hello those students and welcome to your physics lesson. Today we'll be looking at the laws of motion that were founded by Sir Isaac Newton. You can guess that obviously these laws are the Newton's laws of motion. We'll be looking at the three of them and the formula that comes from the second law of motion. So let us start so that we don't waste much of your time. The first law of motion simply states that a body continues in its state of rest or motion in a straight line, provided that it's not disturbed by an external force, or simply a body continues in its state of rest unless it is acted on by an external force, or a body continues in its state of uniform motion in a straight line unless it is acted on by an external force. Now, this tendency of a body maintaining its state without being changed is known to be inertia. In the picture I'll just show you, we'll see how the first law of motion can be seen in real life situations. I know we know about the game of pool. Yes, so in the game of pool, we know that there's a white ball and other different types of balls that are hit, put in that should be put into or sent into a pocket so that the one who finishes their balls first wins, right? Yes. So now in the game of pool, I want you to notice that there's this white ball. So as we can see in this picture, these balls are at rest. So these balls that are at rest won't move unless they are acted on by an external force. So a body continues, they will continue in their state of rest unless an external force acts on them. The white ball will obviously only move if it's hit by the stick, and these balls that have made a triangular shape here will only move if they are struck by a white ball. So you see, basically how the game of pool works comes from the first law of motion. With that said and done, let's go to the second law of motion. The second law of motion states that the rate of change of momentum is directly proportional to the force causing it and acts in the direction of the force causing it. But I like to say it as the rate at which momentum changes is directly proportional to the force causing it and acts in the direction of that force. Again, we can find an application, or we can find the way in which the second law of motion is applied in real life. Think of the game bowling. In this game, there's this ball which is called the bowling ball, and those white border-like structures which are called pins. What happens is that the bowler, who's the man in this picture, will roll that ball to hit those balls. So if you can see, the rate at which the momentum will change in this bowling ball will be directly proportional to the force this man applies onto the ball. And you can also see that depending on the direction in which the man pushes the force, the ball might also change its direction, or simply the momentum will also change its direction. So you see, the second law is also very useful in life, or plays an important role. Now let's look at the third, which is the last law of motion. It's the simplest, and I'm sure you can't forget this one. It simply states, for any action there's an equal and opposite reaction. For any action there's an equal and opposite reaction. Think of a swimmer. If you know how to swim, you obviously know how to turn in water and do all those things. Yes. So today we'll be talking about how the third law of motion is applicable when a swimmer is swimming. Here's a picture showing a swimmer pushing their self against a wall. So this swimmer will move in front immediately they push their feet against the wall, right? Yes, this is because there will be an equal and opposite reaction from the wall. When the swimmer pushes their feet, a force is going backwards. Now there will be an opposite reaction, so meaning there will be a force going forwards, which is causing the swimmer to move forward. So I'm sure you've understood the three laws of motion. Now let's look at the formula that comes from the second law of motion. If you can remember, the second law of motion states that the rate at which momentum changes is directly proportional to the force causing it and acts in the direction of that force. So our force will be directly proportional to the change of momentum. Now, if you can remember, there's the word rate which is in the definition of the second law of motion. So that word rate simply tells us the change of momentum will be divided by time. And how do we get change? We subtract the initial from the final. So simply force is directly proportional to the final momentum minus the initial momentum divided by time. Now, momentum is found by multiplying the mass and velocity. It's found by multiplying the mass and the velocity at which an object is moving. So with that said, we know that mass does not change, right? So even if it's final momentum, the mass will be the same with the mass in the initial momentum. And so only the velocities of the final momentum and initial momentum differ. So we can say the force is directly proportional to the mass times final velocity minus the mass times initial velocity, or simply mv minus mu divided by t. Now, we can see that the mass is common in both the final momentum and the initial momentum. So we can factorize the top part and it will give us F is directly proportional to m multiplied by v minus u over t. Now, if you look at this representation right here, the F is directly proportional to m multiplied by v minus u over t. We can alter the arrangement but still have the same meaning. So what we do is we get this m and put it as the denominator of the f, or the divisor of f, and we'll have f over m, so that when we have a symbol meaning directly proportional, we'll just have our v minus u over t on the right side. As you can see, when we multiply m by this part, we go back to this. So now I want you to notice that this formula on the right side is simply the formula for acceleration, right? Yes, so we can say F is directly proportional to A. When we reach this point, it will be very simple to say F is directly proportional to mass times acceleration. Now, as the formula is right now, it can be very difficult to use it to solve, right? So now, to get rid of the sign which is meaning directly proportional, we need to put in a number that will always be present on the right side, or simply a constant. And so to symbolize that constant which we don't know yet, we'll just say F is equal to K multiplied by M multiplied by A. So that number we'll find as K will always be present on the right side of the equal sign for us to solve. Now, if you check the definition of a Newton, you'll find that a Newton is simply a force that gives a mass of 1 kg the acceleration of 1 meter per second squared. By virtue of saying a Newton, we simply mean 1 Newton, right? So our F will be 1. And we already know through the definition that the mass will be 1 and the acceleration will also be 1. And so simply saying we're multiplying the K and 1 times 1, which is obviously 1. So K multiplied by 1. So simply 1 is equal to K multiplied by 1 times 1. If we simplify what's in the brackets, we'll find that our answer is 1, and 1 multiplied by K will give us K. And so the value of K, or the constant, is 1. Now, anything we multiply by 1 will simply give us 1, right? So the formula from the second law of motion is simply F is equal to M multiplied by A. It's very essential to remember this formula, as it will be very useful in the sample question that we'll be doing right now. The question reads, what is the force required to increase the velocity of a mass of 4 kg from 2 meter per second to 10 meter per second in 2 seconds? So there's an object that has mass of 4 kg that's moving at 2 meter per second. Now, the question is being asked, how can we increase the velocity of this mass to 10 meter per second in 2 seconds? The question sounds complex, but before we do any interpretation, let's just get our data that we've been given. We're required to find the force, so we don't have the force. Our mass is 4 kg. Our final velocity is 10 meter per second. Our initial velocity is 2 meter per second. Our time is 2 seconds. Now, in the formula we just derived, we've got acceleration. But as we can see, in this question, we haven't been given acceleration. So what do? Well, it's simple. We will find the acceleration. How, you may ask? Remember I told you acceleration is equal to v minus u over t, the expression we had earlier before we simplified. Yes, so we'll use that. A is equal to v minus u over t, and replace the values of v, u, and t. So A will be equal to 10 minus 2 divided by 2. 10 minus 2 gives us 8. So A will be equal to 8 divided by 2. And our acceleration will be 4 meter per second squared. Now we have the acceleration. So we can use our formula F is equal to ma to find the force that is required to increase the velocity of a mass of 4 kg from 2 meter per second to 10 meter per second in 2 seconds. So F is equal to ma. Our mass is 4 kg. So we'll multiply the 4 by the acceleration we just found, which is 4. And our force will be 16 newtons. So that's how we can use the formula we just derived from the second law of motion in question. Sometimes you won't need to calculate the acceleration, it will be given. So that's all for the topic of Newton's laws of motion. and look out for our next physics lesson, which will be covering another topic or a part of a topic.